start for today. Okay, come. Let's start with today. Anyway, something is say first regarding the number of lessons we have. Okay, then I just clarify that for a moment first. Okay, today, right, we are doing Chem morning revision questions. Okay, so this is on top of the tutorial questions that I gave you guys the last lesson. Okay, because I feel that Chem morning is important enough for us to do this worksheet. I actually initially intended on skipping this lesson with you guys because I thought, because we need to catch up as fast as possible, right? But I feel that this is a good lesson for us to cover. It's a good worksheet for us to do in class. So then, because of that, I realized there's a little bit of a discount in terms of the lessons. Okay, no worries, there's no problem here. It's just that I just need to inform you guys. Okay, we are currently here this week. Okay, these are the catch-up lessons. Okay, so let me tell you first. Okay, the normal lessons is basically what the rest are currently doing right now, like doing the normal syllabus. So they're currently on this thing called gaseous state. This week they're going through gaseous state part 2. Okay, so we are here right now. So on Wednesday, I'll show you guys for the first lesson of gaseous state. So you notice that this week we still haven't caught up yet, right? Okay, but next week, when they are doing gaseous state 3, and then when we do 2 lessons, right, then we will finally catch up with gaseous state 3. So that's the idea. So we next week, right, still have it's the last time that we have 2 lessons next week. Then we are finally caught up with the rest. Okay, initially I told you guys that this week is the last time because I actually initially didn't want to go through this lesson with you guys. I thought it's important enough. Okay, so we need to cover this today. Okay, so anyways, I'll leave that there first, in case anyone else comes in afterwards. Okay, but anyways, today we're gonna start on questions. Okay, so let's talk about a few things first before we dive straight into the questions. Okay, when it comes to chem bonding, right? Okay, there are 3 main core ideas. Okay, the first core idea is structure and bonding. Okay, as I mentioned before, right? Okay, let's just leave this here for the rest of this. Okay, structure and bonding is arguably the easiest part. It's really easy to identify in exam, right? Okay, the second one is VSEPR here. Okay, as we mentioned before, right, this one requires you to refer a little bit to notes. Okay, because for now, you high chance won't be able to memorize all the different shapes, all the different bond angles. Okay, but finally, you're going to take a look at intermolecular forces of attractions. Again, I think that this is the most important part of the chapter because it explains your physical properties. So today we're looking at all these applications. Okay, remember your melting points, your solubility, and all that. Okay, I won't be going over all those again because we went through last lesson. For today, I just want to focus on one more thing, which is time management. Okay, so time management cannot start 1 month before the exam. You must start now. So I'll show you guys a few things first. If you look at question 1, right? Question 1, there are 2 parts, total 3 marks. Now, I'll tell you first, 1 mark in the exam, your by right allocated 1.5 minutes. This is the ideal amount of timing you should give yourself. So if you slowly include this into your internal clock, right, you should roughly gauge how much time you're supposed to allocate to a question. Okay, for question 1, we are given 3 marks. So by right, we are supposed to take 4.5 minutes, right? Okay, but sometimes I might vary the timing. I might make it shorter, I might make it longer, depending on what I feel the question requires you to do. Okay, not every mark requires exactly 1.5 minutes. Okay, sometimes it's faster, sometimes it's slower. Personally, I think question 1, right, it can be faster. Okay, that's why I give you guys 4 minutes. I'm gonna time you guys. Okay, so I just need you all to start now, basically. Okay. So start now, 4 minutes. Okay, try to do the first 2 parts. Should be just enough time. Sama for bullying. mark. 4 minutes left. Okay, so if you're wondering part 2, right, what cyclohexane is, I'll just tell you first. Cyclohexane is C6H12. You can take that down. That's all you need to know for the second question. I'll give you guys another 30 more seconds. Try to tidy up your answers by then. And let's stop the time right there. Okay, so that was 5 minutes, which is honestly fine now, because if we exceed 4.5 minutes now, it's totally fine. I don't expect you guys to hit the time. Okay, but yeah, that's what I had so far. I think these are very good questions. Okay, let's start with I3 minus. How do we draw I3 minus? Okay, so one thing is I need you all to include the bracket. Some of your answers, you all forget to include the bracket with negative charge. Okay, then I realize you draw only one I. They're asking for I3 minus. Okay, so 3 I's. Okay, now can I ask you all, right, a negative charge, what must you do? Can you remember? You add an electron to the what? The more electronegative atom, correct? Okay, for some reason, I always realize that when people do this question, you all tell me add to the side atom, add to the central atom. Not exactly. I never told you guys any rules regarding center or side atoms. Okay, just remember that. Okay, I only told you guys more or less electronegative. But in this case, right, unfortunately, all of them are equally electronegative. So do you add it to the center or do you add it to the side? Any clues here? Okay, so I never actually told you guys, if you see a scenario like that, so you can tell me at the center, you can tell me at the side. So let me show you guys two possible solutions. I never say it's correct or not. Say it's possible. What I'm going to do, I'm going to add an electron to the center guy first. Okay, so this guy has 7 electrons, 7. Now the center guy has 8 valence. Okay, 7 valence can form how many bonds at the side? 1. Okay, so we draw a single bond on both ends first. Okay, how many more do I need to free up in the center? 6 more, right? 8 minus 2 gives you 6, so I have a total of 3 lone pairs. Now, is IB able to hold this many electrons? Yes. Okay, so we are like 4 or something, we are 5. Okay, so this looks like a correct answer because all of them fulfill the octet rule. Okay, but I can simply say right, that this is actually not an answer. Now you might be asking yourself why, right? Okay, we'll come to that in a bit. The answer to this question, right, is that you must actually add it to the side item. So in other words, I must have 7, 7, and then the side item has 8. Now there's a reason for that. I never taught you guys this reason, so I'll come to that later. Now we just draw first. I'll ask you, 8 valence electrons can form how many bonds? 8 valence can form a, what's it? No bonds? Cannot be no bonds, right? It is a dative bond. Okay, take note. 8 electrons, you can only form a dative bond. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. So all dots in this case just give to the atom in the center. Now I know I told you guys before, dative bond is usually center give to the side. But that's a bit different. Because the side atom has 8 valence, right? You must give it to the side. Okay, the atom on the left hand side is 7. So it's the same thing. I have 1 bond. How many more do I need to fill up in the center? 2. I need to fill up another 6 more, right? So 6 more electrons will look something like this. Now you might be asking yourself once again, right? What the hell is the difference? Because up here, the center atom has 2, 4, 6, 8, 10 electrons. Here also 2, 4, 6, 8, 10 electrons. Then what the term is the difference? It looks like both are possible answers. But over here, right, only the second answer is correct. Okay, now, right, can someone tell me why the second answer is correct? First one is wrong. Okay, let me show you guys a clue. The clue, right, lies in the question. The question mentioned that in order to form I3 minus, I2 reacts with I minus to form I3 minus. Can someone now tell me why, right? It is only possible for you to form the second version. Can someone see why already? Do you notice I3 minus is you take I2 and you add I minus. I'll ask you, I minus got how many electrons? 8. I2 is made up of 7 electrons, right? So that's why, guys, I minus is an external species coming in using a dative bond. So this should be 7, 7, 8. So why is 7, 8, 7 wrong? Because this implies that the 8 electrons is going to sandwich itself in between the 2 7s, which doesn't make any sense. Have you ever seen something sandwich itself in between the 2? No. Okay, that's why the first answer looks correct, but it's wrong. Doesn't make sense. Okay, so tricky question. Your school also like to test you guys this N3 minus. This came out for almost 1 or 2 years ago. Yeah, okay. N3 minus is known as an inside ion. One of the Chinese times. So I think this one, right, I haven't seen it in a while, but then the rules are not as strict. So if they test I3 minus in the exam, they will have to give this to you guys. You know, if they somehow never give, maybe the question is a bit shit, but then you must know about this. If you're wondering what I3 minus is, okay, you all know when you all fall down as a kid, right? Then your mom apply the iodine solution. Yeah, okay, it's basically I3 minus. Not I2, not I minus, but it's I3 minus. Okay, it is a common species you will see more and more often. Okay, all good so far? Okay, now, so that's for part 1. Okay, let's move on to part 2. I don't think this is very difficult. I told you guys cyclohexane is C6H12. What does that tell you? This molecule is a what kind of molecule? Remember, when it comes to solubility, we need to identify whether the molecule is polar or non-polar, right? Okay, so this C6H12 is what? Non-polar. Because I mentioned to you guys before, carbon and hydrogen are non-polar. So the whole molecule obviously must be non-polar. Water is a polar molecule. And because of that, you already see non-polar and polar don't mix together very well. That's why it's probably insoluble. That's what's mentioned in the question. Okay, all you need to do is to identify the interactions. So I'll ask you, all right, this non-polar is what interactions? Okay, non-polar can only have ID. Polar has hydrogen bonds. Okay, something more special. Don't tell me PDP. Okay, water is hydrogen bonds. So what's the interaction between the two species? Red color. Right. Okay, non-polar and polar, do they like each other? No. If you don't like someone, the attractions are going to be very weak. The weakest form of interaction you all know of is ID attractions. You can even describe it as weak. So here, the answer just need to fill in the blanks. Actually, it means from the weak ID attractions between C6H12 and water is what? What to compensate? What's the correct word for this? Not enough, right? Insufficient. Because it's insoluble, right? So it's insufficient to compensate for the energy required to overcome the, they just fill in the blanks. IV attractions in C6H12 and hydrogen bonds in water. That's all we have here. 2 marks, rather okay, rather easy to get because we've seen this scenario now. All good? Okay, that's for question 1. Okay, let's just slowly scale up from here. Here onwards. Okay, good. Okay, if let's say we're gonna now try question 2, today we try as many questions as possible, right? So let me tell you the time allocation first. Question 2, I want you all to do the whole thing. The whole thing is 4 marks if I'm not wrong. And for 4 marks, I'm gonna times 1.5. So I'm gonna give you guys 6 minutes for question 2. Okay, so 6 minutes, just start now. It's not a very tough question, right? Two and a half minutes left. 1.5 minutes left. Yeah, give you guys 1 additional minute and study up whatever you need to. For like 20 seconds left, then I'll go back. Okay, come, time's up. All right, so that was about 7 minutes. It's fine. You overrun by 1 minute, it's honestly considered okay. Okay, and just want to talk about something, right? Okay, so if you let's talk about the first question. Okay, so usually, right, the first question I tend to see a lot of people spending quite a lot of time on it. You have to understand, right? It's only 1 mark. And for 1 mark, you should take maximum 2 minutes to finish this question, which sounds a little bit ridiculous. It looks like there's a lot of things to do, actually. Okay, because you need to draw a structure of carbon dioxide. You also need to draw SO2 structure. And after that, you need to explain. Okay, all that within 1 or 2 minutes, right, is quite ridiculous. So let me show you guys, right, some ways to speed things up. There are some common structures that you need to do. Okay, I don't know whether I tell you guys this already, but let me just say it again. Carbon dioxide is a common structure. Okay, so anyways, okay, carbon dioxide is a common structure. Okay, so I suggest you guys next time you see carbon dioxide, you just remember the shape straight up. So you don't have time in the exam to draw, then after that you go and think about the shape and all that. Carbon dioxide is a linear shape, please take note. Remember the bond. Other common shapes include water. Water has a bend shape. I do not want to see anyone drawing water as a linear shape anymore. Okay. Other than that, we have NH3. NH3 is a very common trigonal pyramidal shape. So look back. Okay, and then finally we have like CH4. CH4 is also considered another common structure. So what I'm trying to say is this, for this second question here, right? All these 4 structures are considered common structures that you kind of already need. These are your default structures here. Okay, like you think of tetrahedral, right? You should think of CH4. That's like first. Trigonal pyramidal, you should think of. So these are the perfect representations of each shape. All these are just to speed things up. Okay, again, you only have 1 mark. 1 mark is very, very little. And I see some of you guys write a bit too much for 1 mark. Okay, so 3 lines, if you take 3 lines, 4 lines, right, that's a bit too much for 1 mark. So a bit more about time management. Okay, this kind of question, right, we're trying to spot for this thing called red flag intuition. Okay, what's red flag intuition? Basically, we will eventually build this up. There's only some time. Okay, not very fast. You need to know when to skip a question. If you think that you can do the question, then you spend so much time, right? Over a 1 mark question, you're going to end up not finishing the paper. Later, as you can see, some of the 1 mark questions here are very easy to get compared to this 1 mark here. So that's how you know, right? You must see when a question is not worth the time. That's what I'm trying to say. So here is one of those questions, but no choice, we still need to do here. Okay, SO2 looks like this. Okay, so make sure you draw it out first. The bond angle should be 118, but they put it approximately 120. Your job is to compare and tell me what's the difference. Now, this is okay, they ask you to explain the difference, right? What should we do here? Immediately, you look at carbon dioxide and SO2. Why do they have different bond angles? Because they have different configurations, right? Okay, this guy has 2 bond pairs and 1 lone pair. This guy has 2 bond pairs, 2 lead. What should we be discussing here? Bond angles, the differences in bond angles must be explained using the different repulsive strengths. Can you all tell me what's the main repulsive type over here? What's the repulsion called? SO2 is lone pair bond pair, right? How about here? This one is bond pair bond pair. And as we mentioned before, if you look back at your VSP EPR theory, okay, which one is stronger? Which repulsion? The first one is this. This one is definitely stronger than this. You all can see if this repulsion is stronger, it's going to squeeze the bond angle a bit smaller. That's the answer already. So I don't want you to write too much. What you need to tell me is this. Okay, the lone pair bond pair repulsions in SO2 is stronger, okay, than the bond pair repulsions in CO2. And that's pretty much your 1 mark. Don't need to write too much really. 1 mark is really not worth your time to write too many things. So I say again, right? You just need to mention the repulsions and you compare the strength. That's it. That's your 1 mark. If your head a bit itchy, down does a bond angle of SO2 is smaller. I mean, if you write this, okay lah, good lah, but then it doesn't give you extra marks. So you write this for your own reassurance. Okay, can? Yeah, that's it. Don't write too much. Okay, but anyways, just now I just missed the first question. Now we just refer to the recording. Then just do the first question. That's it. Okay, can? Good enough. Okay, so this 1 mark, worth it or not? I would say not very worth it in the exam. Okay, if they give 2 marks, then definitely spend a bit more time to do this. Okay, so let's move on to the rest of this question. Okay, the rest of this question is talking about this thing called Van Acker triangle. Have I ever taught you guys this? No. Okay, there's no such thing in our syllabus, but it's very easy for you guys to study on the spot. Okay, easy application on this. Later we look at the hard application. Okay, you're going to study this, and you must know what these numbers represent. If you give an example, you must go and figure it out on the spot. Okay, I'm sure you all know 2.75 represents the average. This one explains the difference. So all you need to do is repeat the same thing. For carbon dioxide, okay, carbon dioxide is 3.05 and 1.1. Okay, maybe I see a little bit of your graphs. Some of your graphs draw a little bit wrong. Okay, your graph, right, should lie, if I'm not wrong, it should lie somewhere here actually. Yeah, okay, it should lie somewhere there. Does anyone need help for the calculations? Okay, because I see that your graphs never draw properly actually, never draw correctly. And what did you thought went wrong here? Oh, you meant the calculation, oh my gosh. Okay, don't I thought you guys plot wrongly or something. Okay, so hang on. Okay. Wow, you're gonna expose me like this. What the hide it? Wow, God damn it. So recording some more. What the get it, yes. Wow, this guy come in, you all see right? Hey, how one? Guy come on. Shut the hell up. Get out of my class, boy. Who are you? Get the hell up. Wow, holy, that's embarrassing. Might as well show the recording. Okay, so anyways, this one, right, your graph should be here. And I want you all to go and plot CO2. Okay, don't go and put a cross there, don't do anything because yeah, they might be a bit strict on that. Okay? Any issues? Yeah. Okay guys, part 2. How do part 2? Okay, they're actually nice enough to tell you what point C represents, right? Okay, point C represents ionic bonds. And they're asking for the type of bonds in A and B. So what's the answer here? Guys, what does A represent? Okay, what do you get? Okay, good, metallic. Okay, so A is metallic and B is covalent. Now, how do I derive these answers? Now, number one, if you're going to write ID attractions or all that, wrong instantly. They ask for type of bonding. Please highlight that. Okay, bonding, come back to your core idea. It is your structure and bonding, not intermolecular force. Okay, how do we know that? Honestly, it's not very, very difficult because you look at the graph. What's the similarity of A and B? A and B both have no electronegativity difference. Agree? Okay, so what does that mean if you have no difference? That means both atoms are the same, right? Okay, it could be a covalent bond, but it could be a metallic bond also, right? So we are not sure yet. We need to look at the difference in electronegativity. We need to look at the average electronegativity. Okay, if you have a low electronegativity, what does that imply? You're on the which side of the periodic table? Low electronegativity. The left side or the right side? Left side, right? So left side contains all your metals, so that's why it's metallic. Okay, you might want to write down a bit of explanation. Because what if they ask you to classify your answer? Okay, so let's prepare for the scenario. Okay, if metallic bonds are, you can just justify metallic mean low average electronegativity, which are basically your metals on the left-hand side of the periodic table. The metals left side. Left of periodic table. Okay, can? Covalent. Okay, so covalent makes more sense also, right? Because how do you explain this? How do you know it's covalent? I mean, by process of elimination, you know it's covalent, but how do you know that? Okay, guys, what do we do? High electronegativity means which side of the periodic table? Right side. Okay, so if you have high average electronegativity, that means you're on the right side, which contains all your whites. What does the right side contain? Non-metals. And guys, non-metals usually form covalent bonds. Okay, that's in the event where they ask you to justify all these things. Okay, can? Right, then finally, last question. Now, the last question should be easier, but I want to recap a concept that I've gone through with you guys before. Okay, take a look at this. Al2O3 is what's the answer? More than Al2S3. What do you get? Okay, you all should get it correct already, I think. Okay, more ionic. Okay, there are two ways to do this question, and the wise way to do this question, right, is to use the graph. Guys, this guy died doing this graph. Okay, he spent his entire life doing this shit, right? And then let's use it, let's make it useful. Okay, so as you can see, our comparison is between O and S, right? Okay, and this is about electronegativity. So O is more or less electronegative than S. More. Okay, you don't know, they even nice enough to tell you here. Okay, if you are more electronegative than S, that means what? Very simple. All you do is go upwards. Can see? If this is a more electronegative atom, the difference has to be larger. Larger means you go up. Go up. That's why you're going towards the ionic side. So more ionic. Can see that? Say it up. Difference in electronegativity is larger. Okay, can? But I want to use this to go through a concept that we have gone through sometime in the middle of this chapter. Okay, so I want to talk about that. I want you guys to try to recall, what concept is this? Now, are compounds ever completely ionic and completely covalent? No, right? Over here, they already say sometimes they are more ionic. If this guy is more ionic, it means it's less what? Less covalent. Do you all remember what kind of bonding is this? What do you call that? A mixture of ionic and covalent is intermediate bonding. Can you remember? Okay, so we try to explain using that method. I want you to write this down somewhere. Go and find some empty space where I write this down. Okay, don't write it on the next page. You need that page for working. Okay, so let's explain why it is more ionic using the explanation. Okay, you can flip to your notes also. Okay, go and find the intermediate bonding chapter, and we shall use the factor there to discuss. Guys, am I comparing the cation or the anion? Clearly, it's the anion, right? And do you all remember what's the factor when we talk about the anion? Anion must talk about ionic radius. Good. Just for recap purposes, cation must talk about what? Cation must discuss the charge density. Okay, so it's two completely different factors. I explained before already. Okay, let's talk about this then. Okay, so O2 minus has a larger or smaller ionic radius. Smaller. Okay, good. It's above in the periodic table. So O2 minus has a smaller ionic radius than S minus. Which means what? Okay, what does that mean? So remember how intermediate bonding works? The cation will pull the electron cloud to itself, right? We use the word polarize. If you have a smaller radius, that means are you more easily polarized or less easily polarized by the cation? Okay, can refer to your notes, yes, less easily polarized. We're going to look at my phrasing. The electron cloud of O2 minus, don't do and tell me just O2 minus, is less easily polarized by Al3 plus. Okay. Now, if you are less easily polarized, that means what? If you pull the electron cloud less, that means is there more electron sharing or less electron sharing? Less. Okay, so Al2O3 has less electron sharing, which also means less what? Sharing is about covalent property, right? So does less covalent character. And does that explain this question? Guys, if you have less covalent character, alternatively, you are more ionic. So it links back, right? So you notice all these things you actually learned before. But of course, if you use this method in the exam, right, you're just being stupid because you are really wasting a lot of time. Okay, do not ever use this in exam unless they ask for the explanation. If I were to modify this question, the next part I will include explain using this particular example. Force you guys to explain. Okay, but now to that, okay, the wiser decision is to use a graph. It's faster. Okay, can? Okay, go ahead on the keywords. So smaller ionic radius, electron cloud gets polarized. Okay, then less sharing, less covalent. Any questions? Okay, you write it at the back. If you write it at the back, just make sure you make a note to yourself, say that refer to the back for the other explanation. Okay, so one little question here can explain a lot of things. Any issues so far? Okay, so what we're going to do now, we're going to move on to the next question. And the next question, right, is question 3. Right, this is where things get a bit more challenging. This is a Huakong prelim question. Okay, so I tell you guys what to do. I'm not going to time you guys for this question. Here is mostly to understand how this works. So we will pretty much discuss this together. Okay, so what I want you to do, you'll do part 1 yourself. Part 1 can be done. Okay, I clarify a few things. Okay, then I'll let you all try part 1. Okay, we do that first. All right? Okay, read through it first, then I'll tell you all a few things to do this question. Because some things you never learned before, right? Okay, so I'll tell you off some stuff first. Number 1, what's ethanol? I don't expect you all to know what ethanol is now because this is an organic concept. It's CH2, CH3, CH2OH. Okay, that's the molecule. Okay, and just to make things clear, you know what all these zigzag lines are in the structure? Do you know what that is? You know? Okay, just know these zigzags represent carbon atoms. Okay, because if they keep writing CH3, CH2, it's going to be super messy. So they draw zigzag instead. You will learn this in organic next time, but now you just need to know carbons. But guys, carbons bonded to what? Okay, carbons are bonded to hydrogens. So all these are okay. You see my diagram here. Don't look at the notes here. Look at the board. 1, 2, 3, 4, 5 little pointy parts, right? That means 5 carbons. So the pointy part is a carbon atom. Hydrogen is all invisibly bonded. So over here, right, carbon have 3 more hydrogens just attached to it something. Okay, there's a lot more, but they're all invisible so that it looks a bit nicer. All you need to know, guys, I say again, this zigzag line just represents carbon and hydrogen. That's it. Okay, carbon and hydrogen will be. Everything else they will draw out one. So with that said, okay, then we can try this first. Okay, we'll give it a try. Okay, take your time for the first part. This question I'm not going to time you guys, because this one we need to slowly think. Just to draw a hydrogen bonding diagram, I know you've learned before, just in context of a bigger molecule like this. Okay, so you just remember all the criteria that I taught you guys about, right? Okay, then you just go and draw on that diagram, right? Don't need to draw this molecule again. Okay, just go and use the molecule that's printed for you guys already, and then you just draw the ethanol bonding with it, right? How's it? Good. Okay, something like this, hydrogen bonding diagram. But that's for ethanol. Right? You just need to draw an ethanol like somewhere here, then you try to attach it. Okay, come on. We'll do each question together. Okay, so don't move on to any other question yet. We talk about part one first. Okay, so can you remember what's the criteria for hydrogen bonding? There's two criteria, right? The first molecule must have what? Remember what we mentioned? First molecule, hydrogen must be bonded to F, O, or N. Either one is okay. Okay, then the second molecule must have what? Yes, okay, you must have a lone pair of electrons on FON. Okay, so your job here is to identify who's molecule 1 and who's molecule 2. Guys, look at this lipid molecule. Is it 1 or 2? It fulfills criteria 2, right? Because you notice that there's a lot of oxygens with lone pairs, but none of the oxygens are ever bonded to a hydrogen atom. So go and take note, lipid fulfills criteria 2, which means ethanol must fulfill criteria 1. Does he fulfill criteria 1? Yes. You can see there's an O bonded to an H, so we know that ethanol fulfills the first criteria. And because of that, we can just draw a hydrogen bonding diagram. Okay, there are a few answers. Okay, let me show you a few. Okay, so I want you all to show me the OH bond, then just bond it to CH2CH2. You know, something like this. Okay, if you don't follow the shape here, I think it's no problem. Okay, that's not really the point of this factor. Okay, but there is a shape on oxygen, so I just follow that as well. Anyways, okay, what I want to see right is that this OH bond must have a set of partial charges. Okay, because as you can see here, okay, partial charges must exist in pairs. If there are partial charges here, there must be partial charges here as well. So carbon, oxygen, I think this is a carbon atom. Okay, I know you're not very used to it, but all these like pointy parts are carbons. So carbon to oxygen, that is a partial negative, partial positive. Okay, partial charges done. Remember the three criteria. Partial charges are the first only. Second one, I need to see the lone pair of electrons on F or N. In this case, it is this guy that I need to see the lone pair of electrons on. Make it like bold enough for me to see. Okay? And then what's next? Last but not least, I need you all to label the hydrogen bond. So this is the intermolecular force. So I need you guys to draw this. So O and H, they attract each other. You have to label this as the hydrogen bond. That's it. Okay, can? Now, is this the only possible place where you can form the hydrogen bond with? No, right? As long as you have a lone pair of oxygen. So guys, you can choose this guy, this guy, every single one of these oxygens can. But let me show you what if you choose an oxygen with a negative charge. Is that possible? Okay, let's just check. Again, an oxygen with a negative charge also has a lone pair. So it can just directly attach itself to the H on the ethanol. Okay, so once again, I need to see that why is it attracting this guy? Because this guy is a partial positive, partial negative. Show me the lone pair, and then you finally label this as your hydrogen bond. Okay, you only need to draw one of these guys, but let's just say you draw the second one, you can put that inside as well. Okay, now do I need to put partial charges here? Is oxygen more electronegative than phosphorus? Yes, because remember FON, O is the second most electronegative. But over here, there's no need for you to put partial charges because why? Because there's already a negative charge on oxygen, right? So the negative charge already allows it to attract the partial positive charge. So if you put the partial negative charge, sure, never mind. But if you don't put also, never mind. Because it can already attract. But here you must show. Because there's no negative charge on this oxygen, so you must show the partial negative charge. That's why they can attract each other. Does that make sense? Okay, so that's for the first question. You have learned hydrogen bonding before, but now it's just for a more complicated looking molecule. But your fundamentals are still the same. Any questions? All good, Can. Okay, very nice. Okay, and with that said, right, okay, we will then, just tidy up your answer first. Okay, do whatever you need. Okay, then those are okay, right? I want you all to start reading the second part of the question. This one not easy, okay, we will do this together. Okay? So you think about it first, okay, don't need to write anything yet, because your phrasing will probably be a bit difficult here. Okay, just read the question, think about what's happening. I'll ask you a few questions to guide you all later. Right? So take a look at it first. Okay, keep in mind, this one's about washing hands. I'm sure you've seen the question. Okay, so there's a bit of real life application. There's a bit of real life like common sense inbuilt into this question. So use that like common sense to help us over here. Okay? Because we're trying to translate common general knowledge to a more specific knowledge. Okay, to more like intermolecular forces. Okay, can? Right, so you read the question already, right? Okay, let me ask you guys one thing first. How many players are there? How many species are involved in this question? Can someone tell me? Okay, good, 3. Okay, it's very simply why there's 3, but just to clarify this, soap and lipid, that's 2 already. Soap and water. So soap, lipid, water. Think of a virus is lipid. I'm sure that the first part of this question. Okay, can? Alright, so don't get confused. Okay, so what's happening? Let's go with the questions flow. Now guys, you can clearly see soap and lipid must form interactions. Now guys, imagine this. Your hand has a virus. You use soap on your hand. Okay, clearly the soap must attach to the virus, right? Ask you again, what's the interaction between soap and lipid? They have to form some sort of interactions with each other. If they don't form interactions, can soap get rid of the virus on your hand? No lah, that's a shit soap, right? Okay, so you have to make sure that they form some sort of interactions so that you can get rid of the soap plus the lipid together later. Okay, good. Okay, so what I want you all to take a look at is the lipid and soap. I want you all to now identify what interactions exist between these two molecules. I erase all the hydrogen bonding stuff up, right? Just take a look at the lipid molecule. Can you all tell me what interactions exist? Any possible answers? We have learned 3 interactions, right? ID-ID, PD-PD, and hydrogen bonds. Okay, you just need to check all 3. First question, is there hydrogen bonds between these two guys? F? F or do it? Remember the 2 criteria for hydrogen bonding, right? Lipid fulfills the second criteria. That's what we mentioned earlier. Does soap fulfill the first criteria? No, it doesn't. So hydrogen bonds are out. So guys, is there PD-PD attractions? Have, right? Because why? So this part over here is polar, correct? This part is polar because of the highly electronegative oxygens. And they also have a lot of oxygens here. So all these are polar. They can form PD-PD attraction. So let's take note of this. PD-PD attractions because the molecules have polar like segments inside. But the reason why this question is difficult is because the molecule is that big, right? Is PD-PD the only interaction? Okay guys, what other interactions are there? ID-ID, right? Why? Why are there ID-ID attractions? Okay, don't tell me that all molecules have ID-ID, that's why. Okay, that's not a very good enough reason. Okay? If you take a look, guys, the polar portion, I'm only focusing on oxygens, right? But what are we neglecting? We are neglecting all the zigzag lines, right? Which are made out of carbon and hydrogen. Carbon and hydrogen, are they polar or non-polar? They are non-polar. And because of that, right, guys, you have to acknowledge that these non-polar, long-length carbon chains, right, can also interact with each other. You see the soap particle, there's a reason why they draw so many zigzag lines, even more than what I drew on the board. It's because it's to show that there are significant enough ID-ID attractions. They draw so big, it's so that it's significant. If it's a bit only like one line, then okay, maybe not that significant. Okay, but there's a reason why they print so many freaking lines. Okay, they don't have this thing. Okay, but over here they print so many to show that the ID attractions are for the non-polar regions of this one. So you have to understand, in a huge molecule like this, it is possible to have multiple interactions. You have a polar portion here, yes. You have a non-polar portion here. That's ID-ID. All good? Yeah? Right. Okay, so that's the first part of the question. Done. Any questions so far? Okay, let's move on to the second one. Soap and water. So guys, that's the third party already, right? Soap and water, what kind of interactions do they form? So let me just draw water beside soap. Can you tell me what interactions are these? These are not that difficult. Hydrogen bonds, good. Because soap has the oxygen with the lone pair, that's the second criteria. And water has the O bonded to the H. So soap and water has hydrogen bonds. And guys, you have to think about it. It must make sense in real life also. Guys, I ask you, soap and water, should they have strong or weak interactions? If you want to use water to wash away your soap, right? That means they must form strong attractions with each other, right? If they don't form strong attractions, then you use water and soap, right? Then the soap still in your hand. Actually, it's annoying, right? Okay, so that's a shit soap, right? So understand, it must make sense in real life also. Strong interactions so that water can wash away soap. Okay, so I ask you a side question. Water and oil, the interaction strong or not? No, you all know water and oil are not soluble, right? Okay, but you use oil and washing detergent, that one strong. Okay, oil and washing detergent can get rid of the oil, right? That's how you know they are strong enough to get washed away. Okay, and So that's a very interesting idea. Sometimes you wash your oily plate with soap, then you use water. Water can carry on both. Okay, it's all about interactions. The same idea here, guys. Instead of oil, we're using virus. So let's see how water washes away the virus membrane. So let's look at the third part of the question. How does it break up the membrane? How does it destroy the lipid molecules? Guys, if you look at whatever diagram that we have now, can you tell me what can we compare? Two interactions, what can we compare? We can wait. Okay. We compare strength, correct. But what do you say? If you say bond strength, that's wrong. Please never use the word bond strength. Are we talking about bonds here? No, we are talking about interactions, intermolecular forces. Okay, let's be very careful with our words here. Yes, we can only compare strength. Who's stronger? Hydrogen bonds. So guys, if the hydrogen bonds are stronger than in these interactions, that means what? When water washes away your hand, right? Can you see water will take away the soap? Right? Water will take away the soap, and the soap will detach with the lipid virus particle. Does that kind of make sense to you guys first? Imagine, okay, I say again. Water and soap, very strong interactions. So when it washes away the soap, these interactions will be broken. Because it overcomes these interactions, it's stronger. So when these interactions are broken, it will also at the same time break apart the lipid molecule. So with whatever knowledge that we have about intermolecular forces, that's how we explain this. Oh, good. Okay, phrasing wise, I will do it with you all. You all need to understand first. Okay. So what we're going to do now, okay, I'll show you the explanation. It might be a bit long, but no choice. Okay, if it's too short, you can't explain much. So, okay, so for part 2, let's explain. Okay, I answer point 1, 2, and 3. Okay, so you mentioned the attractions. So the lipid and PD attractions between the polar regions. Okay. And ID attractions between the non-polar alkyl groups. So I know you all never really see the word alkyl groups before. Basically, all these zigzag lines, you will learn next time. Now you just write it down first. They are called alkyl groups. This is made out of carbons and hydrogens. Okay? So point 1 done. Next, you tell me soap and water have hydrogen bonds or held together by hydrogen bonds. Okay, but then it goes straight to comparing the strength, which are stronger than the PD and ID attractions in soap and lipid. So the first 2 points are all purely what you've learned. Nothing about the context of the question. Okay, PD is for the polar regions. You don't really need to specify the oxygen. Just need knowledge. ID non-polar alkyl groups. And soap and water have hydrogen bonds which are stronger. So you compare strength. And then now we answer the third point. How do you break apart the membrane? Thus, water will so-called wash away, okay, and break the PD and ID attractions. In between soap and lipid. So the last point, you don't really need to follow my wording very closely, as long as you roughly have an idea, okay? You roughly have an idea of how to link back to the context can already. So wash away is actually a keyword in this question. Okay? You wash away, but you break apart the weaker attractions between soap and that's how you kind of break up the membrane itself. one little analogy that you can think of in your head, right, is this. Okay, you all gonna see the documentaries where the eagle swoops in and takes away the fish from the ocean or from the water very quickly, right? It's the same idea here. Imagine water is the eagle and the soap is the fish. Okay, so the water and it swoops in and takes away the fish, right? So it pulls away the fish from the water, lah. So it pushes it away, and then the interactions just break. Something like that, lah. So it's just kind of a swooping motion. Because you have to understand, right, water, right, when you wash your hand, right, they'll just swoop away, just wash away your soap, right? Okay, so it just pulls away the soap. By pulling away the soap, you also pull away the attractions with the fish. Makes sense? Something like that, right? You can roughly picture what's happening in this food. Okay, tough question. Anything so far to ask? Okay, okay, all good, huh? Okay, we're gonna flip over to the next page. Okay, so on the next page, right? Continue this question now. We have part 3. Part 3 is also slightly challenging, but I want you all to think about it. Think of an answer first, okay? Don't need to write down anything first, because high chance your answer will be wrong. Okay, so think about answer first, then we will talk about it together. Okay, you might have your answer in your head already. So let's discuss. Okay, guys, I've drawn something on the board also. We have a fiber. The most important thing you know about fiber is it's positively charged, right? So the question said, dust. Okay, they treat dust as a non-polar simple molecule. Now, how do they attract the dust particles? Okay, so they have some sort of interactions that they want you to identify. What kind of interactions are these? Do you have any answers? Okay, just suggest whatever that's on your mind, okay, because I need to disprove the answers that you guys are mentioning. Okay, any possible answers here between fiber and dust? Okay, so a lot of the most common answer is ID attractions. I will discuss why that's not the answer also. Okay, so perhaps we start with that. Okay, why do you all say ID attractions? Because you all see non-polar simple molecules, right? But can I ask you again? ID attractions are between simple molecules, correct? But is this a simple molecule? Let's ask ourselves, what exactly is fiber? They only tell you that it's positively charged. What does that mean? Fiber is a what? Is fiber a simple molecule? Do simple molecules have positive charges? No, right? So it is a what? It's simply an ion, right? Okay, so from now when you see actual charges like this, it's called an ion. Agree? So it cannot be ID attractions. Because ID is between two simple molecules. But this is an ion and then a simple molecule cannot be ID. But there's one interaction I taught you guys, right? That's very close to this. You all know what it is? Ion dipole. Yes. Okay, so let's talk about ion dipole for a bit. Okay, this is not exactly the answer, however. Right? So ion dipole, can we recap, right? It's between what species? Obviously, it's between ion and a what kind of molecule? What kind of molecules have dipoles? Polar or non-polar? Polar. So take note of this from now on. When an ion and a polar molecule come together, they can form ion dipole interactions. Agree? But is this the correct answer in this case? Is thus a polar molecule? No. So that's why this question is a little bit more tricky because it's the closest we have is ion dipole, but yet it's not the correct answer. So let's take a look. Okay, let's go back to our roots. When it comes to non-polar molecules, can you tell me how does the electron cloud look like? Is the electron cloud evenly distributed like this or unevenly distributed? So it's like towards one side. Which one is it? For non-polar molecules. Which one? Okay, it should be this one, right? It should be very evenly distributed because there's no dipole. So guys, you take a look at my dust particle. This is the electron cloud of a dust particle. It just looks like that. So should there be any interactions? Do dust particles have any charges? No, right? Because it's evenly distributed. So there shouldn't be any attractions. But guys, simple question. If you take an electron cloud and you put it close to a positively charged region, what will happen? You'll get polarized. Where do the electrons go towards? Left or towards the fiber or away from the fiber? Towards, because electron cloud electrons are negatively charged. This is positively charged, right? So, same thing, guys. The question did say, what if the fiber is negatively charged? How will the electrons get polarized? If this was negatively charged, the electrons will leave, right? You get repelled. So over here, right, your electron cloud of the dust particle should look something like this. Can you see that? The electrons are gravitating towards the positively charged region. So can you tell me what's this charge over here? The left side is a partial negative charge, not a negative charge. Must be partial negative because it's not an ion fundamentally. Okay, that means this guy is a partial positive charge. Can? And guys, with that said, right, can the interactions occur? Yes, because the positive charge and the negative charge can attract each other. So guys, can you all tell me what is this thing called? What is this thing called? Is it a dipole? Okay, this is a dipole, right? But what kind of dipole? Is this a permanent dipole? Was this here since the very beginning? No. When you say ion dipole, right? Polar molecules have permanent dipoles. It implies permanent. But then what is this dipole here called? Can you remember? Induced dipole, correct. So guys, this is an induced dipole. What's the meaning of induce? Is to create on the spot. Is you're influenced by something. Here, this dipole came about because of this guy. It didn't come about. It's not there like permanently, you know. Okay, it's created on the spot. Okay, by the fiber. That's why it's induced by the fiber. So the correct answer to this question is ion dash induced dipole. So if you write ion dipole, it implies permanent dipole, which is wrong. So you must specify here ion induced dipole. Now we never exactly learned this, okay, but the principles behind this I will teach you all before. Okay, how do ID attractions come about, right? I actually mentioned this before also. So to explain this question, right, it's just explaining how the induced dipole comes about. Okay, tell me this. Okay, the electron cloud, okay, of the non-polar dust particle okay, so you relate it to the context of this question. The electron cloud of the dust particle is polarized by the positively charged fiber. Okay? Don't just say positively charged ion because now there's a context. Okay? So creating an induced dipole. And that's pretty much all there is. You don't need to justify the ion portion because that one is obvious. Okay, can? Make sure you draw this diagram inside. I want you to have this diagram in your notes also, in your worksheet. If not, you read this answer in 1 week's time, right? You don't know what I'm talking about, right? Okay, again, the only electron clouds can get polarized. If you tell me that dust gets polarized, they'll penalize. Dust doesn't get polarized. Molecules don't get polarized. Only electron clouds get polarized. Okay, good. So these two questions are tough. Okay, so we get through the toughest question in this entire paper first. Those who are done, you can do the last question. That one is easy, 2 marks. Okay, if you know basic chem bonding, this one is very simple. Okay, so just finish this up. Then right after this, maybe we can take a short break, right? As for structure and bonding, it is the easiest part of chem bonding, right? Just have to specify one each and get 1 mark each. It's way easier to get 2 marks here than to get stuck on the previous question in exam. Okay, that's why I say, right, in exam, you must know when to move on. Because you never know, the questions later might be easier than the questions in front, right? How's the structure? Trimetallic, lattice. Okay, simple 1 mark, easiest 1 mark of your life. Okay, but bonding is what? Okay, metallic bonds, right? Okay, metallic bonds between the okay, you must specify the context in this question. If you just tell me metal cations, that's wrong. It's Cu2 plus cations. Because they specify copper. Now, some of you may ask me, why is it not copper plus? Okay, it's because in the metal it's copper 2 plus. This is the most common oxidation state of copper. Not copper plus, not really. Okay, copper 2 plus cations and what? C of D localized, sorry. Okay. Notice the word valence must be inside. In the first lesson, I very, very clearly highlighted this to you guys. Okay, you must tell me number 1, the context of the question. Number 2, if you don't write the word valence, I'm sorry, you can't get this 1 mark. So the second mark is harder to get. Okay, but this one you have no excuse to get this wrong in the exam. Okay, maybe the second question you get it wrong, yeah, whatever. Okay, but at least now we know. Okay, so far. Can Okay, with that said, okay, later we will continue. Okay, we take a short break first. Okay, then later we try one more final question for this and for the rest of the lesson. Okay, good. Okay, come, let's come back to the notes again. So today we're gonna do one final question. I think it's a very good question. Turn over to question 6. Okay, the first 3 parts alone take up like the next half of the lesson already. Okay, so take a look at question 6. Part A. Okay, let's see. Okay, do part A first. A part 1, sorry. Yeah. Okay, just do A part 1 first. Because there's a structure that I want to talk about. It's a rather interesting structure. Okay, I suggest you all draw out the structure first, then later you all answer the question separately. So there's a few things for me to discuss. Okay, just try A part 1 first, right? I suggest drawing out the dot and cross cycle. Yeah, I'm not timing you guys for this one because if I time you guys, confirm not enough time. Okay, so just slowly draw the structure first and then you slowly try to explain the answer. Right? Question 6. Yeah. first before you all move on to part 2. Because part 2, I have additional instructions for you guys. Okay. Alright, so let's take a look. For part 1, right, at least hope you have the structure in there first. Because explanation I want to go through with you guys. Right, so you must arrange the atoms carefully first. Okay, boron should be in the smack in the middle because boron is surrounded by 3 OHs. Okay, so one here, the other here, finally one last one. Okay, so something like that. Okay, so I hope you understand now. Hydrogen, right, is another atom. So because there are multiple atoms, more than 2, always take note hydrogen has to be on the furthest away from the center. Okay, hydrogen should always be on the very outside. So because of that, boron is surrounded by 3 oxygens only. The hydrogens just put it at the very outskirts of the structure. So with the arrangement like this, all you need to ask yourself is, hydrogen got how many bonds? 1, right? Very simple. So one bond, and one bond settled. Okay, how about oxygen? Oxygen got how many bonds? 2 bonds, right? But I notice that there's 1 bond here, so here are how many bonds? 1 only. Okay, 1, 1. So here just draw 1 bond, 1 bond, 1 bond as well. Fill up everything on oxygen. So oxygen got 6 to fill up. So that's why we have all our oxygens now done. Boron, is there anything for you to do? So you're working your way outwards in. So boron got anything for us to fill up? No, right? Because boron only has 3 valence, take note. Some people e.g. hence go and draw a lone pair here. Wrong. So what I'm trying to say over here is this. Okay, this structure is special because it has multiple central atoms. You all notice? Okay, the first central atom is boron, obviously. But what's another central atom in this structure? It's actually oxygen, right? Because I hope you all realize you are a central atom as long as you are in the middle of 2 other side atoms. So oxygen here is in the middle of H and P. So it does constitute as the center. Now take note now, guys. When it comes to VSEPR theory, okay, remember, VSEPR theory looks at the central atom to describe the shape and the bond angle. In other words, if you are a central atom, you can have shape and you can have bond angle. So here, shape and bond angle doesn't just apply to boron, it also applies to oxygen. So oxygen itself has a shape that you can figure out yourself. Okay, I'll let you all go and try yourself later. But now this question is only asking about the central atom boron, not the central atom oxygen. Does that make sense? Okay, so how do we explain the shape of the central atom here? Okay, let's just without looking at the explanation yet, right? Okay, how do we determine the shape? We must count the number of electron pairs, right? So how many bond pairs are there? 3, and then how many lone pairs? 0. Okay, 3 bond pairs, 0 lone pairs. Trigonal planar, which has a bond angle of 120 degrees. Okay, over here the question is asking about both, so you need to answer both as well. Okay, but this is not the full explanation yet. How do you explain this question? Now take note, guys. They look at the first half of this question. You need to highlight this part with reference to VSEPR theory. What does that mean? Now, if you copy out the VSEPR theory, you're not adding value to the question. So do not copy out. You're wasting your time. What should you be doing? You should be talking about the essence of VSEPR theory. So let's recap. What is VSEPR theory about? Electron pairs want to be as far apart as possible. Why? The whole objective of that is so that, okay, there's as little repulsions as possible. You have to treat electrons as intelligent species. They know how to be as far apart as each other as possible to minimize repulsions. And hence, if there's very little repulsions, that means the compound is very stable. Yeah, that's the essence of VSEPR. So don't copy everything out. Okay, capture the essence. So look at the explanation here. How do you do this question? Okay, first, you can tell me about the bond pairs and lone pairs first. Okay, this is some basic stuff. Okay, so boron has 3 bond pairs and 0 lone pairs. Okay, that's simple, right? Then the second sentence is you capture the essence of VSEPR. How are these 3 bond pairs going to arrange themselves? As far apart as possible, right? So the 3 bond pairs arrange themselves, okay, as far apart as possible from each other to minimize repulsions. Okay, but wait, before that, around the boron atom. So I'm going to specify this. Arrange themselves as far apart around the boron atom. So in order to minimize repulsions. And you can even add in and maximize stability. So that one really captures the overall essence of VSEPR theory. Okay, very, very important point. I'm going to start this second point here because a lot of people don't know how to make reference to the theory itself. Don't copy the definition. If they ask you to state the VSEPR theory, then sure. State means you copy out. Can. Okay, but this reference. Okay, so I want to see minimize repulsions, maximize stability, because they want to be as far apart as possible. And because they're as far apart as possible, what's the result of this? What's the result of this? The result is that they get a trigonal planar shape. Okay, so hence, boron has a trigonal planar shape with 120 degrees. This is a difficult question to earn your 2 marks. In fact, this might very well be a 3-mark question. Okay? Hello? That's it. Not easy to phrase this, so take note. And guys, without further ado, I want you to move on to part 2 already because we still need to move on to part 3. For part 2, right, guys, I have a few instructions for you all. The question only asks you guys to draw the dot and cross diagram, right? But I want you all to also draw the structure with the shape and all that reflected. Meaning to say, for BCl3, go ahead and draw the dot and cross and then draw the structure with the shape included. Repeat the same thing for BOH4 minus. The one that I want to go through is the second one. The first one is very simple. Okay, go and give it a try. Okay, everything, the full package. BCl3 should be quite simple. Okay, BCl3 is like this. Okay, but dot and cross out of the way, right? You're going to draw the actual structure with the shape included. And after you draw the shape, right? Okay, can you all also write down the name of the shape plus the bond angle? Write everything up. Okay, because the more you write, the more you start to remember. Okay. where H is right there. Here's the exercise that we did in the notes. Okay, draw the shape, bond angle, and the shape itself. So BOH4 minus roughly looks something like this. Okay, this is the existing BOH3, right? You just need to add another OH minus. I hope you all realize, right, that if you take BOH3 and you add a OH minus, you can get yourself BOH4 minus. Right? So the additional thing here is the OH minus. So how do we add that inside? Okay, first of all, you need to ask yourself once again, right? The minus charge means what must you do? Add an electron to the most electronegative atom, which is oxygen. So we're going to add to this oxygen here, because the other oxygens are all the existing ones. So this oxygen has how many bonds? How many electrons, sorry? 7 valence. 7 valence electrons can only form one bond. And the one bond is clearly with the hydrogen here. How do you bond with boron then? Okay, dative bond. Dative bond here 1, 2, 3, 4, 5, 6. Then is a 7th electron. That's how it's done. Why is there a dative bond? Because I hope you all realize over here, right? Boron only has 6 valence electrons, which implies it has a vacant one. What's the term for it? Boron has only 6 valence, so it has a vacant orbital. Remember? If you have a vacant orbital, it means you can accept a pair of electrons via a dative bond. That is, after all, the criteria of dative bonding. That's that. But what's more important here is I want to see the shape being reflected in your answer. Okay. Guys, remember, there are 2 central atoms, boron and oxygen. So I want to see 2 shapes. One shape with respect to boron, the other shape with respect to oxygen. So go and try this last part, right? So some of you all just write OH, right? No, I want to see the O bonded to H. I want to see the shape on oxygen also, right? Don't just write OH. Huh? Okay, let's go through this because we need to move on to our final question for today. Right? So guys, can you tell me what's the shape on boron first? One thing at a time, it is tetrahedral. Now this is not a lone pair, this is a dative bond. A bond is a bond pair. Okay, so I want to see a tetrahedral shape like this. Now take note, one of them is a dative bond. The dative bond should be pointing from O to P. Like that. Okay, so I see the tetrahedral shape reflected here. Now guys, what's next? You notice oxygen also central atom, right? So what shape does it have? Two lone pairs and two bond pairs gives you a band shape. So I need to see a band shape over here. Band. Something like this. Guys, I need you to understand, right, that for these kind of structures, only the central atoms you need to draw lone pairs. The side atoms don't need to draw lone pairs. So since oxygen is also considered a central atom, I need to see the lone pairs here to kind of show the band shape. Boron is a central atom, but it doesn't have any lone pairs, so that's why I never show any here. And let's say, let's go and draw the whole thing with the negative charge. Remember to go and write down the shape of each atom. So boron is tetrahedral and oxygen is band. Go write down the bond angle while you're at it as well. Okay, what's the bond angle of a band? Take note, there are two band shapes, but this band here is 105 degrees. Tetrahedral is 109 degrees. Okay, go write all this in so that you will start to make this a part of your memory, right? Okay. Any issues with this? Okay, if you're okay with this, right, please move on to part 3. Okay, part 3, I need you to try this. This question you might need to write a bit long now because they only give you 4 lines, but I can tell you, you might need to write more than that. Okay, because it's quite a bit to write here for part 3. Okay, so I'll give us some time to try part 3 and then we'll go through this together. Right? This question asks you to refer to structure and bonding. So you need to tell me the structure and bonding as well before you explain the melting points. Okay, include that in your answer. try to follow the answering format here. Okay, I'll just figure out some of the compounds first, right? Then we discuss together. Okay, we're gonna fill in the blanks for all these, for all the blanks here. Okay, but this is the rough answering format that we should use. Okay. Now we discuss this together, right? Because there are some things that we need to talk about before you can even look at this question. Okay, melting point questions. Okay, so melting point questions are application of physical properties, right? It's an application of intermolecular forces, right? So over here, let's look at how we compare melting and boiling points of simple molecules. For that, you guys need to identify the structures of the compounds first. BCl3 is a what kind of structure? What is it? Is it like giant metallic, giant ionic, or what's the class of structures? Okay, take note, you all have drawn BCl3 just now. It's just made up of covalent bonds, so it is a simple molecular structure. How about BOH3? BOH3, is it simple or is it a giant or what is it? Okay, you drew BOH3 just now. BOH3 is also a simple molecule. So basically, both of these guys are simple molecules. So that's why we need to use this idea to explain our answer. Remember, melting and boiling points of simple molecules need to use intermolecular forces. Okay, and last but not least, this guy, what is it? This guy is a giant ionic compound, right? Because it's sodium plus and an ion, so it's an ionic compound. So we can fill our structures into our answer first. These two guys have a simple molecular structure, whereas the last compound has a giant ionic or giant ionic lattice. Okay. And then what's next? Okay, we have to go into our simple molecules, right, and compare its melting points. So later I'll give you time to compete. Okay, let's take a look first. BCl3 and BOH3. Now remember telling you guys, when you want to compare the melting points of simple molecules, what's the very first thing you must compare? You remember? The very first thing you compare is the electron cloud size. Okay, so electron cloud size is that we use the MR to compare the size, right? So can you take a look at these two guys and tell me who is bigger? Who has clearly a larger MR? Okay, notice B and B is the same, 3 and 3 is the same. So that's why we just need to compare CL versus OH. You look at the data book here, CL is 35.5, right? Whereas OH is 1. O plus 3 is only 17. Okay, for some reason, I think a lot of people tell me this is bigger because O and H is multiple atoms. So compare MR, I said that from the start. So it's clear that BCl3 is larger. Now remember, if BCl3 has a larger electron cloud, what's that mean? Follow the explanation. Larger electron cloud is more easily polarized, right? So what does that mean? BCl3 has stronger ID attractions. Can you remember all that? Okay, I'm putting it here because guys, does this make sense in the context of this question? If this guy is stronger ID, does he have higher melting point? No, it doesn't. So that's why you can't use this explanation here. Now I'm not saying this is wrong. BCl3 is indeed larger, so it indeed has stronger ID attractions. But somehow it's just not as significant as other factors outside. So guys, it's quite clear that electron cloud size cannot work. So we need to go to the next factor. Can you remember what it is? The types of intermolecular forces. Here we compare the strength of the different types. So let's see whether this works. BCl3, what's the interaction here? You look at the structure of BCl3 that you drew just now. BCl3 is polar or non-polar? Non-polar, right? BCl3, Cl is more polar than boron. So you have partial negative all the way. But it cancels out in all directions. The dipoles cancel out. So BCl3 is a non-polar molecule, which is held by ID attractors. Now your answer, right, goes straight to the intermolecular force. You don't need to tell me because it's non-polar. Cut some words. You don't have that much time to write so many things anyway. Okay? So you're not writing an essay, you're just writing to the point. So non-polar molecule ID attractions. Now we try BOH. Okay, so go and draw in BOH3 as well. But hope you remember O has a band shape. but B here will have trigonal plane. Okay, that's how BOH3 looks like. Can you tell me, is BOH3 polar or non-polar? Okay, it is polar, right? Now some of y'all will say O and O will cancel out, agree? So I don't draw anything. O here, cancel out. But you have to understand, here I have polar, polar, and polar. Can you see that? Do you all notice all the arrows are pointing downwards? So there's no arrows pointing outwards to cancel out the dipoles. So that's why overall BOH3 is a polar molecule. Okay, I can put in the partial charges, you can do that yourself. Can you see that? Okay, so BO is polar, but it cancels out all three here, so I don't draw anything. You just draw out the rest. Now guys, what's the interaction here then, if it's a polar molecule? Hydrogen bonds, good, because there's no bonded to H, right? So it's not PUP here, it's hydrogen bonds. Now guys, does this make sense in the context of this data set? Hydrogen bonds are stronger than ID-ID attractions and require more energy to overcome. This explains the question. So guys, hear me out. Do not just think that this is wrong here. It is correct that BCl3 is stronger ID-ID, but the hydrogen bonds are way stronger than that. Because of that, that's why this is the more significant explanation for the data set. And that's why you use this only in your answer. You don't write this, it's not random. Okay then? Yeah. So that's what we have here. Do you remember what's the final factor? I don't care you go to Trinity, so you don't need to go to the final factor. But in case you need, right? What's okay? Good. In case the intermolecular forces just nice are the same type, then you must look at the factors within each type. Okay, but anyways, we don't need here. So we look at the last compound. As you can clearly see, giant ionic is ionic bonds. Ionic bonds are definitely stronger than intermolecular forces, so the melting points are a lot higher. So this is very simple to explain. Okay, so it has a giant ionic lattice, it is held together by ionic bonds. So I answer structure and bonding first. Between the anions, between Na plus and BOH4 minus. Can you see that? I specify the cation ion at that. Okay, then you just compare. The ionic bonds are stronger than the hydrogen bonds in BOH3. So I compare with the previous interactor. Okay, don't you tell me ID-ID attractions are. Because if hydrogen bonds are stronger than ID-ID and ionic bonds are stronger than hydrogen bonds, then it makes sense for ionic bonds to be stronger than ID-ID. So I don't need to mention it again. Okay, and that's why I put here thus requiring the most energy to overcome. I suddenly use a slightly different language here, most amount of energy. Because it is the third compound, so you use this kind of language. So I would say 2 marks for this is not worth it. Okay, I want to say that, okay. This one, it should be 3 marks. For you guys right now at this stage, if you test this in exam, it's 3 marks because of the amount of time you require to do this. Okay, but because this is a prelim question, right? Chem bonding by the time you are J2 prelim should be a very easy topic. That's why they only give 2 marks for this. Okay, for now, 3 marks now. Okay, I would think it's quite decent. Okay, all good? Okay, so if there are any questions, any more questions? Okay, don't have, right? We are going to tell you guys what's the homework for this also. Okay, so I know I gave you guys chem bonding homework as well. Again, that one I'm not rushing you guys to finish it or anything. Okay, so I am giving more homework here because I think it's necessary. Okay, homework I'm going to write here. Okay, so this question is question 6. Finish up the rest. There's not much to finish also. Okay, but then you also do question 4, question 5, question 8, if I'm not wrong. Basically, it's everything in this worksheet except for question 7. Question 7 is a little bit not important. It's just a dot and cross diagram, which we have drawn before, so I don't really care. Okay, but the rest of the questions are good, so finish up those. Again, you don't need rush this. Okay, you can send me the tutorial first. This one you take your time. Okay, no deadlines, just make sure there's quality answers. Okay. If you guys send me any of your tutorials right now, I wouldn't be able to mark yet because of my J2s have exams this week. Your seniors have exams. Okay, so that's why I have to mark their papers first. Yeah, and the next lesson is on Wednesday. We will start on a new chapter already. So data state. Okay, so yeah, remember, take note. Oh, I haven't told you just now because it came in. Next week still have the 2 lessons because we have this. We did this today. That's why next week is the final week where we have both Monday and Wednesday. Right? Then the following week we arrange separate. Right? And yeah, so this coming few lessons will be data state and maybe a little bit of revision mixed in. Rather more chill topic. Okay, Ken? Hello, that's it. That's it for today. Right?
I think